and also the author of the paper with the title of Deep Learning-Based Spatial Temporal Human Action Recognition and Localization System, together with my supervisor as an author too, named as Pak Nugraha Priyatama. He is also from Bandung Institute of Technology. But before that, to begin with, I want to discuss a little detail about the background of this paper. As we can see in this modern world, there are lots of people walking down the streets and CCTVs are anywhere to be found. But the question is, are we confident enough to able to recognize all the anomalous behaviors that take place, especially in 24/7? For example, like people fighting down in the streets, fighting each other in the streets, passing out, or even running on the street, or even fighting on the streets. Yeah. And thus, I propose the system that is able to localize human actions spatiotemporally. But before that, we need to understand what means by spatial temporal action localizations. Spatial means that the system is able to localize, is able to detect where the actions is where the action is occurring in a frame. Meanwhile, temporal means that the system is able to know when the action starts and finish to be done. And both spatial temporal terms means that the system is able to extract both spatial and temporal information at a time. And the advantage for the system is able to recognize and localize multiple human actions simultaneously at its frames. And the next one are the reference that I use in this paper. The first one is YOLO, you only watch once architecture. YOLO utilizes both 3D CNN and 2D CNN to complete its task with to localize human actions, spatiotemporally. YOLO paper stated that 3D CNN is better at predicting when the actions start to occur and finish to be done. Meanwhile, 2D CNN is better at predicting where the action is taking place in a frame. And YOLO paper is also using channel fusions, CFAM channel, to harmonize the information gained from 3D CNN and 2D CNN result. And YOLO paper, the output of YOLO paper that it stated that it is able to achieve an accuracy of over 80% for UCF datasets, which is considered a state-of-the-art architecture. And the next reference I use is YOLO, you only look once architecture. This is YOLO is a special is also state-of-the-art 2D CNN architecture, and the basic architecture of YOLO is depicted in this slide, and is used in this paper. And it is best to detect object. And the next reference I use is ResNet. ResNet is a 3D CNN architecture that introduced cardinality concept that makes this architecture is better at extracting spatial and temporal information at higher accuracy, and is also considered a state-of-the-art architecture. So the next one is the pipeline flow of the proposed system. There are 3 flows. Starting from the first one is human object bounding box localization extraction using YOLO architecture, and the second flow is human action bounding box localization and action classification using YOLO architecture, and the third flow is bounding box filtering based on IOU calculation on both first flow and second flow bounding box results. The next one is the flow for building machine learning model. Here are the standard architecture here are the standard flow in building machine learning models, starting from dataset gathering, preprocessing, dataset splitting, and training and validating model. These are the number of the training clip and validation clip that is used in this in training the system, and also the dataset source are NTU, RGBMD, and JSMDB. For building the model, NTU, RGB plus D introduce these following datasets modalities, including joint points, joint estimations, puppet flow, and including puppet flow and joint estimations, and also puppet mass. In NTU, RGB, and D, we can see there are about 120 action class classified in this dataset in over 100,000 videos. But among these 120 action classes, are only to about 8 actions to be used to train this system. Okay. So the next one is JSMDB. JSMDB introduced this following datasets modality, including puppet flow, puppet mass, and joint positions. JSMDB has a total of 21 actions classes within 928 video clips. And among these 21 actions, I only took one action to be classified with run actions. The next one is dataset splitting, which is this table shows that the number of training frames and validation frames that I gather for to train the program to train the system. And the next one is training and validating model. For the training part of the deep learning architecture, this is the second flow of the system which I trained. It is differentiated into 3 main parts, including spatiotemporal feature extraction using ResNet architecture and facial feature extraction using YOLO architecture. And it is also used CFAM mechanism, channel fusions, and it is based on gram matrix calculations formula. And this is the method of my training process. For this ResNet, I use a transfer learning method from pre-trained model that is available in YOLO site. And the second one is the YOLO. I also use the pre-trained, which is sourced from the darknet. Because this is both a pre-trained model, that's why I freeze all of the layers of these both architectures, except for the last 3 backward layers for these architectures. And here are some information, including the downsampling numbers, values, and variables values during the training process and building model process. Again, during the building model process. And the next one is the loss calculations. For the localization loss, I use MODS L1 loss formula to calculate the loss. And for the confidence bounding box, I use MSE loss calculations. And for the confidence class and for the confidence of its action classes, I use focal loss calculation formula. And this the next one is the environment. It's the environment which I use for training the program. I use Kaggle platform, and I trained to a total of 22 epochs. And the next one is building, and the next one is testing the deep learning architecture. This is some output, example of the output that I use YOLO, only YOLO as the architecture. As we can see here, there are lots of false negative happen here. There are no peoples, but it's categorized as action taking place. And based on those results, I introduce these two additional flows to improvise the system. This is the first flow is to localize human object, and the third flow is to, and the next flow is bounding box filtering based on IO calculations that is implemented to YOLO bounding box result and YOLO bounding box result. The aim of the third flow is to decrease false negative results. And these are the environment specification that I use during the testing. I used the laptop and these specifications, and also we can see here that the frame MAP is successfully increased from 41.6% to 33.84%. That is happen 2%, 2 more percent is significantly improved. And now I would like to show you some of the example. For example, we can see here that the bounding box, false negative bounding box are eliminated, and the result is considered a success because this is classified as falling down because this person is soon fall down. Okay. Then the next. So now here we arrive at the conclusion of this paper. This paper successfully increased the significance of 2 more percent of frame MAP result, but the FPS is result to be lower for half value, for about half value. But we can see in this example there are lots of false negative. For example, like this blue bounding box is eliminated in the system, and this so many bounding box are also eliminated. And this marks the end of my presentation. Thank you very much.
Okay, thank you, Jesslyn, Nathania, for your interesting presentation. Okay, audience, please, if you have any question, you can ask directly to Jesslyn, Nathania, or you can write your question here. Type your question in the chat here. Any question? Okay, Jesslyn, I want one question. In your experiment, your model can recognize human action, only for one human action. Now, can your model recognize for multiple person action?
Oh, actually, okay. It's my turn to answer your questions.
Yes.
Okay, actually my system is not only able to recognize one action at a frame, but it is also able to detect multiple actions. For example, like that in this slide, and we can see the example here. There are lots of this police, the police actions and this for person actions are recognized in my system. So it's not only able to detect one actions at a time.
Can your model predict what's next action will do by the human?
How can I predict the next actions going to be happened?
Yes.
Okay, so during this model, this architecture model, we can see here that this input is the depth is 16 frames. That means that the model is able to process 16 frames at a time. Which means when we are at the keyframe 1, we took the next 16 frames. So we are able to detect what action is going to happen next. So this is the method in order to recognize what action is going to happen next, because we took the video longer than the current frame.
Okay. Any question from audience?